Hello friends, in this video we will make analysis for various thermodynamic devices in which flow occurs. Those devices are nozzles, diffusers, turbines, pumps, heat exchangers and throttling devices. By steady flow energy equation. Steady flow energy equation. If you want to see the derivation of a steady flow energy equation, then you can refer to my other video named thermodynamic analysis, various two approaches, system approach and control volume approach, and steady flow energy equation. Okay, so let's start our discussion. So this is steady flow energy equation which we derived in another video. So first we will take nozzles and diffusers. Nozzles or diffusers, both are same thing. In nozzles expands, and in diffuser also the type of nozzles. In the case of liquid flow, so it diffuses the flow. So here pressure drops and velocity increases, and here vice versa. So what is nozzle? Suppose any high pressure chamber, just like steam chest, and there is an nozzle here. So nozzles are very small devices. So just expansion occurs at the nozzles. So here in the steam chest the condition is 1, and after the nozzle the condition is 2. Steady flow energy equation is nothing but Bernoulli's equation. Heat terms are also added in that. So we will write steady flow energy equation for this. So at this is actually left hand side is for 1 and right hand side is for 2. So let's discuss about the terms here. So H1 plus, look here, V1 is 0 at steam chest, V1 is 0, and Z1 equal to Z2, same datum. Here S2, V2, Z2. So Z1 equal to Z2 and V1 equal to 0. So what we will get? H1, this 0, GZ1 and GZ2 will be cancelled out, plus Q is also 0. There is no heat transfer, only work done. So work done is also 0. So H1 equal to H2 plus V2 square by 2. No heat transfer, no work done. Z1 equal to Z2 and V1 is 0. So from here we will get V2 equal to under root of 2 in bracket H1 minus H2. Okay. Now second we will take turbines and pumps. Both are also same. In turbines expansion work is done. In pumps we do work on the gas. Pressure is increased in that. Turbines or compressors, isn't it? Compression occurs there. So turbines, second is turbines, pumps. What is turbines, pumps? Look, expansion occurs here. Point before the turbine is, this is turbine or pump. So before turbine condition is 1 and after turbine condition is 2. Now let's discuss here. H1, V1 is almost 0. Z1 equal to Z2, that will also be cancelled out. Here H2, V2 is almost 0 as compared to enthalpy terms, and Z1 equal to Z2, that term will also be cancelled out, isn't it? Q equal to 0, there is no heat transfer in turbine, but W is not 0. W, how much work is developed in turbine, that is important, that we will calculate. So let's put H1, this is almost 0, GZ1 and GZ2 will be cancelled out, and Q is also 0. So H1 equal to H2 plus V2 is also almost 0 plus W, that implies W equal to H1 minus H2. If suppose data is given for V1 and V2, so we have to put it and calculate that also. Then there will be V1, if V1 and V2 also we will take, so W equal to H1 minus H2 plus half V1 square minus V2 square. Look, V1 and V2 are already very less, and as compared to enthalpy terms, and their squares will be very, very extremely less. So this could be safely discarded. But if suppose data is given, so you have to calculate. Okay. And pumps vice versa, signs will be changed. H2 minus H1, because there it is increasing. Okay. Now third we will take heat exchangers. Heat exchanger. What happens in heat exchanger? This is suppose cold fluid coming, or suppose in this hot fluid and in this cold fluid, double chambers. So while passing through cold chamber, the pipelines will pass through the cold chamber. So this will become cold. Before heat exchanger, this is heat exchanger. This is heat exchanger. Before heat exchanger, point is 1, and after heat exchanger, point is 2. Here H1, and definitely V1 is 0, and Z1 equal to Z2. V2 is also 0, pipe flow simply there. So let's put no heat. Heat is transferred, but work is not done. W is 0, but Q is not 0. On that Q we have to calculate. So let's put, so H1 plus this is 0, this could be cancelled out, plus Q equal to H2 plus nothing is there. That implies Q equal to H2 minus H1. If suppose enthalpy of H2 is much, means heating is done, positive heat transfer. So this will be, and in our case which I made, it is negative heat transfer. Heat is getting rejected. Heat is rejected. So because it is getting cooled, so it will be Q equal to H1 minus H2. Because this would be minus Q, then in our case it will be minus Q. Okay. Now last is throttling device. In throttling device, so many persons have confusion. What is throttling device basically? Suppose a high pressure chamber is there, and then there is a small opening. If this opening will be earlier it might have been closed, but if it is opened, then it simply expands to this big chamber, very big chamber. So simply expansion took place. So because of expansion, its temperature gets decreased, volume increases, no heat transfer, Q equal to 0, W is not there, Z1 equal to Z2, V1 equal to V2 equal to 0, because there is no velocity at all, just slowly they are expanding. So what we will get? H1, this is also 0, this could be cancelled out, no heat transfer, no work done, so equal to H2, this all are 0, H1 equal to H2. So in throttling device we get H1 equal to H2, that is isenthalpic process, because enthalpy before the expansion and after the expansion will be same. No heat transfer, no work done, so enthalpy didn't go anywhere, isn't it? So this is all about this video. We discussed several thermodynamic devices in which flow occurs by steady flow energy equation. Thank you.